this talk is called No Fate But What We Make, Doing Intrusion Prediction, and it's about doing an alternative method of prioritization for CVEs by using prediction rather than using some of the conventional metrics that we use today. And so first I'll explain why we do that, and I'll talk about what it looks like. So my background is I've been at 6 startups, 4 exits, several security product startups, a couple of larger security companies that you may have heard of, some things that you may have used. Been working on mostly blue team stuff, mostly threat hunting and detection for most of my careers, but I've worked alongside red teams and studied offense a lot in order to get better at detection. So I'd say you really can't be A-list at both, I think, red and blues, but I'm fairly purple, so I'm, and that I think kind of figured into how this came about, like how I was able to do this from spending a lot of time with red teams and studying about offense and how they work and why they make some of the choices that they make. This is the abstract for the talk, but it's essentially what I'm arguing is that a lot of the methodology that we've been using is, well, some of these like exploitability are newer than others. CVSS has been around for a long time. Some of these are newer, some of these are older. But as the volume of this stuff increases, as it is increasing dramatically, some of these methodologies are not working for us so well anymore. Some of them didn't work that well at the volumes we had 10 years ago. And that they're really, I think, only well understood by security teams. I don't think they're not extremely well understood outside security teams. And so that a lot of these are mainly used by InfoSec teams. But even with InfoSec teams, as we'll see, the volume of this it's starting to get past the point where this manual process of humans analyzing CVs one at a time or committees of humans and agreeing on scores and metrics and assigning metrics and scores to CVs one at a time, it's not really scaling anymore. But at the same time, there are some interesting things about the data that suggest that maybe that wasn't the best way to be going about it in the first place. Like it isn't necessarily, a lot of these methodologies that we've been using have not actually predicted the CVEs that have turned out to be the ones that caused us the most harm, that created the biggest fire drills. So basically this is about, what I've done is I spent a lot of time on this last year, tried a number of different approaches, and finally arrived at a model. It's running now, and it's outputting predictions on CVEs. And so far to date, it's generated 25 correct predictions that I can prove were made forward in time. What I mean by that is I wanted to, it seemed to me that in order to publish this, it was important to be able to show that it was real and it's not just something that's made up. So the way I decided to try to prove to you that it's real, that like the predictions are actually being made before they come true, is when the model runs, the output of the model is then published in a GitHub repo where it gets timestamped. And then when a prediction evaluates true, when one of my predictions comes true and a CV does get added to a watch list, is anyone familiar with the known exploited vulnerabilities watch list? So that's one that it's maintained by CISA, which is part of DHS. And it's essentially, it's a list of vulnerabilities that are known to experience significant exploitation activity, enough that they're given high priority in terms of in fact, they even have deadlines in terms of these should be patched or mitigated by this deadline because it's that important. There's that. There are some others. There's a company called Vulnverse that has a list of their own you can subscribe to. But essentially what happens is, so the output of the model gets published in GitHub where it's timestamped so you can see when it was published. And then in the future, when one of those predictions comes true, meaning when one of my CVs that have been rated hot is added to a watch list, then I count that as a provable prediction, right? Because I predicted it before it happened. So it's been running since January 3rd. So far, I have 25 correct predictions as of yesterday, right? So there's two possibilities, right? Either the model is generating correct predictions, or I have a backdoor into GitHub, both of which are equally interesting. But I can assure you it's the former. All right, so I'm going to borrow a page from a CISO I used to work for, and this is kind of fun, but what do you think this number is? Anybody? Say it again?
Number of
total number of CVs in existence, 274,000 as of Wednesday or whenever I pulled this data, right? Okay, so this is what the growth curve looks like. Anyone looked at this before? I only plotted this myself a few months ago, and I was actually surprised. I mean, I knew there was a growth curve, but I was surprised to see this. This is basically what this is plotting is the number of new CVEs per year, and that's remarkable. And I think there's a number of things that are driving, and I think one of the things that's going on is because this started here. Let me make sure these are fit. Okay, so you can see the years. This started around here, and so this started well before we started using things like LLMs and AI and ML-based automation for offensive security art, which we could debate how good the models are at actually finding CVs and developing exploits, and they may not be quite there yet in terms of getting on par with what the bug bounty hunters produce. But I think what happened here is this is where I started getting bug bounties, was in this time frame about a decade ago. It's where we started getting not just bug bounties from bug bounty vendors, but also just inbound bug bounties from just independent researchers. And I think that's one of the reasons that CV development really took off, was that we started paying for them. And I think I'm not sure we realized that if we start paying for CVEs, what we get is more CVEs, but that's what happened. So this was also, this time frame about 10 years ago, that was, I think, when, for me at least, some of the existing process stopped working so well. And what I mean is that in the portion of the first 2/3 or so of the graph prior to the bracket, there was a time when either by yourself or maybe with a small team, even in a fairly large environment, with enough data, you could put together a realistic risk assessment. If you had, say, network data, inventory data, scan results, red team results, threat models, if you had enough data and you had enough time to put that together, you could figure out where the critical attack surface was and which 10 vectors were likely to be where your next incident was going to happen, with enough people and enough time, and people that really like sifting through data like that, you could do it back at that level. And that was like 2016, 17. It was around that time that the scale of this started getting away from us. And I think the volumes we have today, I think it's relatively hard for humans to try to do this with those kinds of manual analysis processes like we used to. And wrong answers only, or right answer is wrong answer is okay. What do you think these numbers are?
Total number of CVEs in 2025 so far, and total number of CVEs.
Close. The number. So the number we have in 2025 for the first 3 months, it's actually larger. But this works out to is, over the last 15 months, we're getting not quite 3,000 CVs per month, which comes out to about 148 per day. 148 per business day, assuming we work a 5-day week. And nobody's doing CVs on weekends, hopefully, although sometimes that does happen, but not often. Assuming a 5-day business week and no holidays, we're doing 148 a day, right? Which is, I don't know that many security teams that can process 148 of these per day in a really thoughtful way. And I think for non-security teams and DevOps teams, I really don't think this is realistic. So in the past, what I did is, a couple of days ago, I just re-ingested CV data from the NVB database again. NVB, because NVD has a lot of metrics. They tend to have more metrics than some of the others that I'm going to use. I only pulled the last 15 months because taking like the whole 20, you can, I mean, with enough memory, you can load the past 25 years into a data frame, but it takes a long time. So I took the last 15 months. The last 15 months is about 44,000. I excluded WordPress because like not for any particular reason other than WordPress is not always relevant to everyone. Like I think out of all the organizations in the world, there's a subset of them are running WordPress, and there's WordPress accounts for, like, if we put those back, there would be a few thousand more. WordPress accounts for a slice of the total number of CVEs. There's just a lot of them. So to try to make it more fair and realistic in terms of what are we actually, like, assuming that we're not dealing with WordPress, what kind of volume are we actually looking at in a typical enterprise? So hopefully nobody saw that. What's this number? It's really strange, actually, that this number is so small. Well, maybe it's strange, maybe it's not, but it's interesting at how small this number is. So that is the number of CVs in the Kev at the time that I ingested it, I don't know, 2 days ago. So of the 270 odd thousand CVEs that we have, 1,300 of them get used the most to great effect, which is about actually less than 0.5% of the population.
I only know that it was 313 at the end of the day on Friday because I have a script that I was working on.
Okay.
So I'm just surprised with myself.
So what's interesting to me about this is that, of those, because there's a great debate. Some people say that, well, we need to patch everything all the time, and honestly, that's hard to do. It's hard to get there. Even if your business stakeholders really want to do that at the cost of other things, it's hard to get there. It takes energy. But even if we could, this suggests that a lot of those 274,000 are actually not the ones that are going to be the one that gets us. It's these 1,300. Now, it's probably not just these 1,300. There are probably a few others that are exploited, but maybe not exploited at great scale sufficiently to land on a watch list. But whatever the actual number is, it's a very small portion of the total. So, and at the same time, this 1,300, it's a much smaller number than conventional processes would tend to prioritize. We would tend, using things like CVSS and EPSS and exploitability, reachability, and all these, we tend to prioritize much more than 0.5% of these. So it's interesting that the offensive actors are choosing and prioritizing these in very different ways, I think, than we are. In terms of, by prioritizing, I mean choosing which ones that they are going to use, which ones they like to use, which ones they prefer. So they're looking at them a lot differently than we are. So this is what kind of started me down this road. This is a quote from, this is again is about 10 years ago, before the growth curve took off to the sky. But even back then, the volume was considerable. And having done a red team and doing a red team retrospective, one of my tech leads essentially made this remark and said, we're not going to 100% patch convergence with a fleet size in the tens of thousands, and we're probably not getting to 100% patch convergence. And this is true, I think, of many organizations. Honestly, getting to, again, in a large fleet, getting to 100% patch convergence is hard. I'm not sure how many people are there, but it's not everyone. But he basically said, look, if we know we're not going, we can't get to 100% without suspending, without disrupting the business and other people's work, or increasing the cost basis of the business beyond what it would bear. If we can't get to 100% with the resource that we have, then what should we do? How do we get to a point where we do a red team and we don't have people taking the primary flags, and we have a red team result that actually looks good, and it doesn't look scary and makes everybody scared. And I think at the time, we don't always have a good answer for this. I think at the time, what I would have said a decade ago, when things were, it was possible to try to figure this out with enough data. It was possible to try to figure out where the critical attack surface was. What I would say is, it's probably not necessary to, if you use a sports metaphor, if you allow it, it's not necessary to block every shot in the game, but what you need to do is you need to block the shots on goal. And so in order to do that, you need to figure out where the goals are, or where the goals are that don't have goaltenders. in our metaphor. And 10 years ago, I think with enough time and energy, we could do that, even at scale. But today, I think it's at these volumes, it's getting harder. So having thought about this for a long time, I've always wanted to come up with a better way to, a better way to prioritize these in a way that has a real effect on the business and people's lives. But two, to try to figure out how to better prioritize these and try to imitate the way that the threat actors are prioritizing them rather than the way that we are, if we could get there. And in terms of what's out there today, so a decade ago, I've seen fleets with millions of unpatched CVEs, large fleets. A decade later, today, in the last couple of years, there are at least some out there with over 1 billion CVEs. And it's not because there's not 1 billion unique CVEs. I mean, there are 1 billion instances of unpatched CVEs across the entire fleet, across a large fleet, right? And when you get to these kinds of numbers, it's kind of hard to decide where to start. So sometimes I think it's overwhelming. It can be overwhelming at these numbers. All right, so let's take a look at what I did is this notebook is in this repo. And this repo is public. And one of the things that's great about GitHub is you can put a Jupyter notebook in there and it will render it for you as if it was running Jupyter, and you can just present it. Like, I don't even have Jupyter running here. So what I'll do is let's just run through some conventional metrics, it's like some conventional prioritization using existing metrics and process. And I'm going to try to make the case to you why that conventional existing process is not working so well. At least that, well, we could argue whether it's working or not. I mean, it's working. It's doing a lot. We're better off with it than without it. So I won't say it's not working. The process is working and it's generating good decisions, but it's not getting us to that 0.5% that are like the super critical of the critical of the critical. It's not how we're going to find those. And so let me try to explain why. So what I did here is I ingested all the CVs from the last 15 months. I excluded WordPress just so that we're not skewing the data just based on WordPress, because not everybody has WordPress. And that gives us about 44,000 in the past 15 months, which again is not quite 3,000 a month, 148 a day. Maybe if you take holidays, it'd be closer to what, I don't know, maybe 100, 175, 200 a day. I don't think we're going to give up holidays. I don't think we're there yet. So then what I did is I ingested the Kev. So in the Kev, when I took the Kev the other day, there were 1,312 in the Kev. And then I looked for matches. So in the past 15 months, there are roughly not quite 200 Kevs that I have detailed data for. And the reason I had to do this, I had to do all this work because in the watch lists don't have all the fields that you'd find in some of the other, like they don't always have things like CVSS, EPSS, exploitability. They have CWE. They have fields, but they don't have every single field. So what I did is I had to do some work in order to find the Kev entries in the first data frame so we could look at all the metrics for those. And so getting rid of not a number values. So for the numeric values, what I did is so some of these metrics, by the way, don't yet have scores in them because some of them don't yet have score metrics that have been assigned yet, just because there's a lot of them, and I think there's a bit of a backlog. So any place that there's not a score metric that came through as a NaN, I set that to 0. And so in terms of metrics, so let's take a look at some basic metrics first. So here's what the distribution of impact looks like this is across the CV population. Yeah. So across the CVs that we have for the last 15 months, there's not really, I mean, there are more at the high end of the impact scale than at the lower, but there's still a pretty good distribution there. But then there's also this, because not all of them have an impact score yet. And then exploitability, again. I would have thought that exploitability would have a much bigger skew, but it doesn't. It's actually the high end of the exploitability scale is actually not the highest bar in the chart. And of course, there's some zero values too. So CVSS is also, isn't that interesting that you would think, we would think that they would be concentrated towards the high end of the CVS scale, like 8 or 10, but they're really not. In fact, the largest candle is what? 5. So there's not really a good, I don't really see any like a good decision. And again, with the zero values, I don't see a good predictor there, a good decision metric. Here what I did is I did a stacked bar by severity and score. So severity is like alerts, low, medium, high, and critical. And again, surprising, right? I would have thought, well, I guess in the general CV population, I guess you kind of expect this, but again, you can see that there's a number of basically none, meaning that they just haven't been given a value yet. All right, so then next. So doing a stacked bar of exploitability by severity. So there's a little bit of signal here, although it's a little weird that there's more volume in the medium combo than the high. And although there is some signal here because, so the number that have both critical severity and a high score, that's a pretty good low number. We're down around 5,000. So that seems like one possibility. So if we have a combination of high severity and high exploitability, that might be one possibility for cherry picking a few thousand instead of a few tens of thousands. But again, at the same time, but not all of these yet, not everything yet has these metrics. So we could probably do some good cherry picking there, but we might miss some. And then looking for just trying to see how these things correlate. So I did some scatter plots. So there's a scatter plot between CVS score and exploitability. And there is a nice set up there. There is a nice set at the top that has a nice alignment. And then CVSS score and impact. There's kind of, there's a lot going on kind of all over the place, but there is a decent sized cluster up in the top right at the high end of the scale. So there is that. So there is some there. And then exploitability and impact looks like this, and not as strong as I thought. I would have thought, I was expecting more correlation, but there are some decent correlations though here. So score versus exploitability works out to a pretty good correlation. And score versus impact. That makes sense because I think score and impact they're kind of cousins. They're very related. And so I think similar kind of thought process goes into the assignment of score that goes into the assignment of impact. And I think impact is probably maybe decided first. And impact, I think, is a primary input into score. The greater the impact, the higher the score. So that makes sense. There's a good strong correlation there. And then exploitability versus impact. A little bit weaker, which I guess could make sense because, well, I guess it could and it couldn't, right? Because how could if something has lower exploitability, how could it have high impact, right? Because if it's not exploitable, then it's not going to exploit, it's not going to detonate, and if it doesn't detonate, then it probably doesn't have an impact. But I think it's also because these are factors that I think may not be considered together. They may not be inputs to each other. They might be considered separately. It also could be that there are some out there there are some black swans out there that could have extremely high impact, but they're relatively difficult to exploit. All right, so now in here, let's take a look at so setting aside the general CV population, let's take a look at the recent CVs listed in the KEV. So the CVs from the KEV from the past 15 months. So impact looks like this. So there's a pretty good impact signal there in that most of them are at the high end of the impact score, which would make sense. Because if they've been watch listed for attention, it would make sense that they've got some impact. And I mean, everything on the KEV probably does have quite some impact. It probably is on the higher side. Exploitability makes sense because I guess it's a little odd that there's some lower exploitability scores here, but because if it's on a watch list, it means it's being widely exploited to great effect across the world, right? And it's not just affecting one organization, but many. But I think what could be going on here is that I guess this kind of aligns with what I think I see in that maybe an 80-20 rule, in that there's a set of exploits out there that are easily exploited, and exploits show up within a day or two. But there also is a tail of exploits that take much more research and development. It takes much more effort to develop them, and those might be outside the capabilities of garden variety threat actors. That might be getting into the territory of professional threat actors working for nation states, or maybe really well-funded ransomware crews, but it might take more significant resources. So that could explain that. CVS, now CVS score has a nice signal. So these watch listed CVEs, they're definitely on the high end of the scale. Most of them between 7 and 10. So that's a possibility. So then what if we take, next, let's just look at some categorical values. So here's the distribution of values in the CWE field. CWE is, somebody probably knows this faster than I do, but it's common weakness enumeration, right? Right. It's essentially, it means what class of software vulnerability does this CVE involve? It's like a category. And there are a lot of these. Like there's SQL injection, buffer overruns, and there's dozens of others. So this one, though, but the thing is, there's not a great cluster distribution here. There's kind of a long tail, but there's also a lot. About 20% do not yet have a CWE, because not everything always gets published. What about vector? So vector means, what's the vector? Is it across a network? Can you do it across a network? Which makes sense that those are that makes sense to me, because if you can, exploiting something remotely is much more usable and much, if you're a threat actor, something you can exploit remotely is much more attractive than something we have to exploit locally. Because if you have to get local to the target, well, that takes time, effort, and energy, but also it means that you really probably can only go after high-value targets, right? Because you just don't have enough people to send to every target unless you're, but there's still like 23% local. A physical and adjacent network is extremely low, which I guess makes sense, because how many cases do we have where somebody actually physically intruded into, I mean, it's not zero, but it doesn't happen that often. So we've got 83-ish% have the network and local vector. So that seems promising. Complexity low, again, makes sense, because in the range of threat actors out there, in the gradient of threat actors between a simple garden variety threat actors and extremely sophisticated threat actors, it's probably not a bell curve. There's probably more threat actors at the lower end. There's probably a lot of threat actors at the lower end of the spectrum and a few at the higher end. And so it makes sense that complexity would be attractive, because more threat actors can just make use of something with lower complexity. Maybe also because lower complexity means faster time to market. If you're a threat actor, it's the lower the complexity, the faster you can bring an exploit to bear. Sometimes speed is a factor, because if it's, depending on what it is, if it's a headline like log, if it's an all hands on deck like a log4j or something where people are really moving fast, then you might only have a 24 or 48 hour window. But most CVs don't move that fast, right? Because we can't have a log4j fire drill once a month, or I mean once a day, but we can't have one once a month really either. It's just it can only happen when there's something that is extraordinary. So privileges, none, makes sense because from a threat actor's perspective, something you can do across a network unauthenticated without privileges. Obviously, you're going to be able to harvest a lot more targets and a lot more victims or something like that versus something with higher privileges. So that gets us again to about 80%. So there's a nice signal there. Interaction, none, again. Simpler the better. So that's 74%. And these, there's a lot fewer none values here too for some reason, so that's good. So we're getting I think some good numbers. And then a confidentiality impact, 88%. I guess that makes sense because a lot of what goes on out there is related to data theft. Integrity, 77%, which probably is a reflection of ransomware. And availability, that one surprised me because if you're a threat actor, how do you make money by crashing people's things, right? How does that benefit anybody? So I don't know why availability, I don't know why there's so many, but I suppose, there are exploits that will crash or hang a service or leave it in an unusable state. So there's a number of population of exploits that will affect availability, so that could make sense. All right, so then let's look at, in the CV population, how many CVEs match one of these criteria? Meaning, at least one of those factors is the one that is on the high end of the chart. And so that gives us, it gives us numbers, but unfortunately that matches almost half the CV population from the past year. So that cuts it in half, but being bitten in half by a shark is not much better than being swallowed in one piece, right? So it doesn't necessarily help us that much in the scheme of things. So looking at some metrics between, let's look at metrics like score, impact, and exploitability. So taking the mean, the median, and the standard deviation for those metrics between the entire CV population and the KEV. And then let's see. So there's definite signal here in that the mean scores, the mean and the medians, and the reason I think the reason we've got medians of 0 here is because there's just a number out there, there's a quantity out there that just don't have scores, so they're set to 0. The KEVs are much more likely to have scores, so they have a median. But if we ignore the median for that reason, the mean score for the KEV is actually pretty high compared to the general population. Average score of almost 8, impact of 5. Exploitability is not, you would think exploitability is almost twice the general population, so there's good signal there. So then what happens if we look for that criteria? Or if we plot this first, we can see that there's definitely a much higher average score, definitely a much higher mean score for CVSS in the hot list, in the watch list, and impact is higher, and exploitability is almost twice, not quite double, so that's still higher. So suppose we take the mean and the median values for these metrics, score, impact, and exploitability, and we cherry pick those out of the CV population. How many CVs do you think we get using that? Wrong answer is okay. So if we do that, we can do that, but we still get 15,371, which is just slightly north of 1/3. So we've gone from half of a mountain to a third, but 15,000 is still a lot. So 15,000 is still 1,000 a month, and it's still, you know, more per month, more per day than is probably digestible for it. You know, challenging for security teams, but for non-security teams, I think this is not really digestible. So I mean, when I say digestible, I mean for non-security team, 1,000 per month is still too many. So in terms of what else we can do, so I spent several months last year running models on the data in order to try to see if we could to find another method of prediction. And the comparison of the categorical fields, by the way, is going to be similar. So this is what vector looks like in comparison. And if we say looking for CVEs where the vector is local or network, which is where the watchlisted ones tend to concentrate, though, that doesn't help us because, again, we're back to 48% and 21,000. So we're not getting anywhere remotely near the 1,300 number that. What I did here is just for fun, and we're getting into some pretty heavy data science here, so I won't spend time on this, but you know, your data scientists might enjoy this and probably could do it better than I. But what I did is I ran some statistical tests between the two data frames, and you know, what the values tell us is that there actually are some significant differences between the general CV population and the watch listed CV population. There's some definite statistical difference there if we could get at it. But in order to get at it, I think it's just going to take more work than, well, it's going to take more data science than, and it's going to take a different approach beyond the conventional score-based analysis that we do today. So, whoops. So this repo is public, and I'm running this roughly monthly or so. I haven't run it recently, but I've run it a few times this year. And so far this year, the model has output 25 correct predictions. In that, what it does is it labels CVEs as hot or cold, and it does it in a way that is very different from any of the conventional kind of analysis scoring, any of the conventional considerations, ranking scorings that we tend to use, and what I showed here. In fact, most of what I showed here is actually not what the model is doing. It's doing something very different, and it's using a data set that I assembled by hand. And I think that part of the reason that it's working is because in order to do this, I think it really takes collaboration between security research and data science, because it requires extensive knowledge of both. But what I did is I assembled the data in a way that I think reflects the thinking of the threat actors. And what I mean by that is, why did they choose those 1,300 out of the 274,000? Why those 1,300? I think that, to give a short answer, I think that they look at it. So we look at these and we give them scores and ratings and things like we're a ratings agency. And I don't think that's how they look at them. I think they are actors in an adversarial pursuit. In 10 minutes. And we're almost done. I think that their thought process is not dissimilar to a professional sports player. That they choose the equipment that they like for one reason or another, or because it has served them in the game and on the field, and with that, and they feel as though they've had more wins than losses with that particular equipment, right? And they don't care about product ratings or reviews or anything that they like. Sports equipment probably does have extensive scoring and ratings and review systems, but the players don't really care about that. They care about which equipment am I more likely to make progress in the game and have a win. And so I think that's how they see it. That's how my red teamers look at it, I think. But you have to really kind of spend a lot of time with red teams, I think, to understand how they look at these. but it's really not about, it's really not at all about metrics. It's really more about, I'm a threat actor, I've got a tasking, I've got a target, and I've got actions on objectives, and I've got a target and a timetable, and what can I use, like what is going to get me to my objective in successfully and in the time, the allotted time box that I have. And some of that is, I think some of that is, well, what's worked for me well in the past. Some exploits are workhorses, but like what I mean is that there are some exploits out there that always work. They don't crash the service. They're extremely reliable. And so I think, people keep that in mind. So, but basically what I'm proposing is that if we can do, because some of these predictions have lead time as long as 93 days. The last one I published was predicted 93 days ago that it would be watch listed, and it was watch listed this week. And so, but even with 30 days early warning, if we can, what I'm doing is with these predictions in hand on CVEs, and then with some network attack surface data on like how many of these things exist and where are they, then I can take the cherry pick, I can take the prediction data and I can match that up with what we know about attack surface, and then I can cherry pick, and then I can identify, even just working alone, I can identify what the top 10 most likely next intrusion vectors are. And if we can do that before the exploitation cycle arrives, then we could be avoiding incidents completely. Rather than doing incident response and cleanup, we could just be doing incident avoidance. And so that's what I'm hoping to do. And why do we need this? Well, based on the number of CVEs that we have today and the volume of CVEs, the challenge in trying to process that kind of data volume even for security teams, and the speed at which threat actors are moving. Even 5 years ago, before we started using things like LLMs, threat actors were moving relatively fast. Exploitation cycles often start within 24 hours of a CVE release. Even a decade ago, you would see exploitation cycles within 24 hours. 24 hours is a very fast window to patch. I would say some organizations can do that, but I think a lot of them really can't. But what happens so everybody's doing research on using LLMs and AI for offensive security research now. For exploit development, I think we're going to see probably people trying to do more CVE development. And I don't think, so in terms of how productive this is, I read mixed results. And that it probably is helping existing exploit developers to go faster. I'm not sure yet that it's at a point where a model can just start cranking out CVEs and exploits in like linear time, like 100 times faster than we can. However, I think that we probably will see that in our lifetime in the future. We'll probably see CV and exploit development increasingly automated. And well, if that happens, then there's also no reason that people are automating exploitation cycles with models today, because that's relatively simple and straightforward to do. Scanning, enumeration, discovery, exploitation. So if all of that gets accelerated 100 times or 1,000 times by using models, then all of our manual human response processes obviously are going to be meaningless, right? Because there's just no way we can move that fast. We can't even think that fast. One, because of the contraction in speed, but at the same time, if that growth curve continues, we could be looking at 100,000 CVEs a year. If that growth curve starts becoming, suppose somebody is able to train a model or is able to get a model to start being really productive at CV and exploit development on an industrial basis. If that growth curve, goes to the sky, then I don't think that's on the horizon. I think that maybe in our lifetime. I don't think that's happening next month or immediately, but if it does, then we're going to be in a very different kind of problem space. So questions so far? I think we have just a couple minutes, 5 minutes, yeah.
Interesting modeling. I was curious whether you use the same model to look at like historical stuff like log4j to kind of think like if this model had been kind of applied back then, would we have had a little more advanced features and all I work for a cybersecurity company, and this is something very fascinating for us, where we might be able to get some more design of time.
Mm-hmm.
But I was curious whether, one, because you talked about the scales, right? Like with these scales, even if you are having a very high prediction, the number of CVs that are going to get on the watch list are actually only going to be increasing. So it's kind of a second part of the question. The first is whether this could have predicted something like the log4j, how hot it got. Second, with just the sheer volume, would it still be, with this model as is, still give us enough headroom to kind of patch those like actual critical ones that might.
Mm-hmm. So it's running at 99% accuracy, and loss is below 1. It's a 0 point, I think it's got very low loss. It is correctly labeling. So I've only run it back to January 2024 because it takes a while to run this model, and even just ingesting the data takes a while. But I do want to go further back because Log4j was in 22, right? 2022, I think, like January, February. It was about 3 years ago. Based on what I'm seeing over the past 15 months, it will predict. So it has correctly predicted 25 so this year, but it also is correctly labeling what's on the KEV going back in time as far as January 24. If I were to say go back 5 years to 2020, that would take a little bit more work. But I believe that I'll try that. So I'll try running calendar 22. We'll almost certainly get a hot prediction for Log4j, and a number of others that year too. Yeah, so the accuracy is very good. The accuracy is good enough today to put this to work, and so that's what I plan to do. The repo is, by the way, if you want to know where to find these, I'll just put it back on screen. Okay, it was in here. Did I lie? Well, it's right. Sorry, yeah, it's this blue text up in the bottom, up the top right. Basically, it's if you Google for Cyberdyne Ventures on GitHub, what that is it's a think tank. It's a group of about 24 security researchers and data scientists. Any given time, about a dozen of us are active. About a dozen of us right now. There are a number of projects out there, and this is just one. It's in a GitHub organization because it's not just my work, it's many people's work. So I didn't want to put it in my repo. It's called, if you're wondering what it's called, Cyberdyne. It's not easy to find a name everybody likes. So that's the name everybody likes. So any other questions? We're out of time, I think. All right, well, thanks for coming to my talk.